Hi everyone. Welcome to the second half of the lecture covering phase diagrams. Where I got up to in the last part was explaining why phases are important and the basis for their existence thermodynamically. I covered their premise, that they can be unary, as if they will describe a single component over variations of temperature and pressure, or multiple components with pressure constant and temperature varied, binary for 2 components and ternary for 3. Like I said before, we're only going to stick to binary systems in this course. And these are important because they inform on properties of the various engineering alloys available and their provenance. We left off looking at a binary isomorphous system, one which changes from liquid at high temperature through some intermediate mushy zone consisting of liquid containing some solid, and then finally a completely solid phase. I also said that this was quite rare to have a metallic system do this. But there is one that we can use, the copper-nickel system. It has a singular solid phase, denoted here with alpha, which indicates there is complete solid solubility of nickel and copper, or vice versa. Complete solid solubility is very rare because it requires atoms that are similar in size, valency, preferred crystal structure, and electronegativity. Let's have a look at the intermediate temperature T0. From the first part of the lecture, I showed that in this region one can get the composition of the liquid and solid that is present here. Let's review some of the features here and introduce some new terms. As before, liquid is L, and it is bound by the liquidus line. This is a locus spanning all compositions that inform the maximum temperature where solid crystals can coexist with liquid in thermodynamic equilibrium. The solidus is the locus of this temperature that below which a temperature is completely solid under equilibrium conditions, very slow cooling. In this case, alpha starts to form as soon as the temperature starts to decrease below the liquidus, and the material is completely solid once crossing the solidus. For this system, alpha is a solid solution of copper and nickel, where the copper and nickel sit interchangeably or substitutionally in an FCC crystal structure. Let's examine what the composition is at 1250 degrees Celsius and 35 weight% nickel and copper. We can read the composition of liquid directly by noting where 1250 is on the liquidus, and conversely the same for the solid using the solidus. These are annotated as C sub L and C sub alpha, respectively. We can now say that for an overall composition of 35 weight% nickel and copper at 1250 degrees Celsius, there are 2 phases present, liquid with a composition of 32 weight% nickel and a solid with 43% weight nickel. The overall composition has stayed the same, but there's been a shift in the distribution of nickel between the 2 phases. As I explained in part 1, this is because the Gibbs energy can be further decreased by doing so, rather than forming just solid and liquid. As it turns out, this means that we can calculate the proportions of each phase present as well. The proportions are represented by mass fraction as captured by weight. The overall mass is comprised of alpha and liquid as decided by their compositions. We can then write out expressions for this as per the bottom right. I've also put on graphically what these 2 equations mean for calculating these mass fractions. We can leverage the overall amount of nickel in our copper to calculate the mass fractions of each phase. For the mass fraction of liquid, it's the difference between C alpha and C naught divided by the difference between C alpha and Cl, and the mass fraction of solid would be 1 minus this. Conversely, we could use the mass fraction of solid. It would be the difference between C naught and Cl divided by the difference between C alpha and Cl. This approach is called the lever rule, and it works for all binary systems, as we shall see. Let's go ahead and apply the lever rule to our circumstances. Writing out the specific expression with values read from the phase diagram for the mass fraction of liquid, we end up with a result of 0.74. Or 74% of the overall material will be liquid at 1250 degrees Celsius. The mass fraction of solid will be the remaining 26%. Note that we can somewhat validate our answer by inspection of the phase diagram at this point in composition. It is quite close to the liquidus line, and it would make sense that there would be more liquid than solid here. Let's now look at a more complicated binary system and the application of the lever rule. At the outset, this system may seem significantly more complicated. It is the lead-tin system, which used to be commonly employed for electrical solder. Let's go through some of the features. As before, it demonstrates a liquidus, but depending on the amount of tin in the lead, it can either start to form the alpha solid phase or the beta. Cooling past the solidus, the solid that forms will not be a solution. Instead, it'll be a mix of these two different solid phases, alpha and beta. You will also note that there is a composition where the liquidus and solidus intersect. With this composition dropping past just below 200 degrees Celsius, the liquid will completely solidify without any intermediate alpha or beta. There is also another construction line which has been included, the solvus. Let's examine these a bit closer. This is a binary eutectic system. Here, alpha is a lead-rich, i.e. more lead than tin, phase with a particular morphology or structure, and beta is tin-rich. The solvus is a line which separates two homogeneous solid phases, and there are two, one for the lead-rich side and one for the tin-rich side. The point where liquid completely converts to alpha and beta is called a eutectic point, and for this system, it's 61.9 weight% tin. Let's look at 2 points of interest where we can apply the lever rule to solve for mass fractions and compositions of each phase. The first, at an overall composition of 20 weight% tin at 250 degrees Celsius, and the second at 40% weight tin at 150 degrees Celsius. I've gone ahead and made all the construction lines that you'll need and highlighted the relevant values of composition. What is of relevance here is what phases are present at these 2 points and what are the mass fractions of each of these phases. Pause the video now and try writing out the lever expressions for each circumstance and calculate these. Now you're ready to see what they are? First off, for the condition at 250 degrees, there are 2 phases present, liquid and alpha. The lever for this condition spans the liquidus and solidus. Putting in the appropriate values for liquid, one arrives at 35% liquid, meaning that the remainder is 65% alpha. This makes sense as the point of interest is fairly close to the solidus. For the second condition, there are 2 solid phases, alpha and beta. The lever for this condition spans the beta and alpha solvus. Putting in the numbers for an expression for beta, there is 36% beta and 64% alpha. Looking at where our point of interest is, we can say that our answer should reflect there being more alpha than beta based on the shape of the solvus on either side of this temperature. Don't worry that you didn't get it immediately. There will be other opportunities to test your knowledge. For example, could you write out the lever expression for alpha as opposed to liquid in the first case, and alpha as opposed to beta in the second? Pause the video here again if you want to have a try or wish to further review. So, phase diagrams only provide an accurate indication of phase compositions and proportions if near equilibrium, or slow heating and cooling conditions, are maintained at all times. In single-phase regions, the composition of the phase must be the same as the composition of the alloy as a whole. In 2-phase regions, we have seen that the lever rule can be applied to determine the proportions of each phase. We've applied the lever rule to 2 types of binary systems. Isomorphous, where a liquid changes to a uniform, singular solid solution phase, as well as the more common but a bit more complicated eutectic system. Even though phase diagrams do not reflect non-equilibrium conditions, they can still be used to explain phenomena that occurs during fast cooling and other solidification phenomena. We'll use the understanding developed here in the coming lectures. Until next time.